Lurking deep within the solar system lies a colossal anomaly, a planet that rolls sideways, a chaotic world with a skewed rotational axis. This is Uranus, the laziest and most bizarre celestial body in the solar system, more perplexing than Pluto, more enigmatic than Saturn. Here, sunlight grows faint and feeble. Temperatures plummet to -224 degrees Celsius. Even the most resilient viruses freeze instantly into ice crystals. Here, 1 year equals 84 Earth years. Each pole endures 42 years of perpetual daylight, followed by 42 years of polar night. This is a frozen world forgotten by time, a mystery that has puzzled scientists for decades. Imagine a planet 63 times larger than Earth, yet tilted on its side like a toppled giant. Its rotational axis leans at a staggering 98 degrees, completely overturning our understanding of planetary motion. This bizarre rotation plunges its seasonal cycles into chaos. The poles bake under 42 years of unbroken sunlight, only to freeze solid in the following 42 years of darkness. This extreme alternation creates a climate unique in the solar system, where polar temperatures are paradoxically higher than at the equator, a realm defying thermodynamic laws. Even more astonishing is that this seemingly tranquil, deep blue planet hosts superstorms raging at 900 kilometers per hour. These storms have persisted for over 30 years, releasing energy far exceeding any Earth weather system, and scientists still cannot explain their energy source. Uranus' secrets extend far beyond this. Possesses 13 rings as black as charcoal, composed of dim matter with minimal reflectivity. These rings encircle the planet like invisible shackles. They remained undiscovered until 1977, when a chance stellar occultation revealed them. Unlike Saturn's brilliant, magnificent rings, Uranus' ring system resembles a cosmic shadow, silently enveloping this contradictory planet. Why does Uranus spin at such an odd angle? Astronomers speculate that around 4 billion years ago, during the solar system's infancy, a protoplanet with Earth-like mass struck Uranus with apocalyptic force. This catastrophic collision not only completely overturned its rotational axis, but shattered its primordial crust and reshaped the planet's entire internal structure. Though Uranus is often grouped with Jupiter and Saturn as a gas giant, its interior is fundamentally different. Its core, comparable in size to Earth, is composed of iron and magnesium silicate. Beyond this core lies a global superocean of ice, a mixture of water, ammonia, and methane. It is these substances that give Uranus its icy blue appearance. But this serene blue is merely an illusion. When Voyager 2 flew past Uranus in 1986, the data it transmitted stunned scientists worldwide. This was an extreme world far beyond imagination. Its complexity completely overturned previous theoretical models. To this day, humanity's understanding of this icy giant remains but a glimpse through a tube. In the exploration ahead, we will delve into every secret of this sideways-lying planet, from its bizarre rotation pattern to its extreme seasonal cycles, from its internal superocean of ice to its persistent superstorms. Are you ready to embark on this breathtaking cosmic journey? Let us together unravel the layers of mystery surrounding Uranus and discover this most unsettling, yet utterly captivating wonder of our solar system. For millennia before the invention of telescopes, humankind gazed at the night sky with the naked eye, recording celestial phenomena. The ancient Egyptians recognized Venus. The Babylonians tracked Jupiter's path. Ancient Chinese astronomers even precisely charted Saturn's position. Yet Uranus remained perfectly concealed from human perception. It became a vast blind spot in our solar system, a secret lurking right under our noses. The fundamental reason lies in Uranus's brightness, which lies precisely at the threshold of human visual detection. Its apparent magnitude reaches approximately 5.6 at its brightest. This luminosity falls just below the limit discernible by the average human unaided eye. Under ideal conditions, our eyes can perceive stars of magnitude 6. Yet this typically requires an absolutely clear, pitch-black sky, and vision sharper than the norm. For most ancient observers living amidst light pollution or atmospheric turbulence, the light of a 5.6 magnitude star was too faint to be easily detected. Moreover, Uranus moves with extreme slowness across the night sky, takes a full 84 years to complete one orbit around the Sun. This means its displacement among background stars is imperceptible. Over the span of a human lifetime, it appears almost like a fixed star. Ancient astronomers identified planets by observing their passage through constellations. Mars' retrograde motion and Jupiter's leaps were distinct markers, but Uranus' near-stationary motion allowed it to successfully disguise itself as just another star among the myriad on the ecliptic. Cultural limitations also played a crucial role. In the era dominated by the Ptolemaic system, the boundaries of the cosmos ended at Saturn. The concept that no planets existed beyond Saturn was deeply ingrained in people's minds. Even if some shepherd or astronomer with exceptional eyesight had glimpsed this faint speck of light on an exceptionally clear night, they would have naturally classified it as an unremarkable star, unaware that it represented an entirely new world. Ancient Greek philosophers may have speculated about additional celestial bodies, but lacked the technical means to verify such conjectures. Ancient Chinese astronomical records were exceptionally detailed, documenting comets, novae, and meteors, yet they too failed to distinguish this slow-moving planet among the stars. Thus, Uranus, a giant planet 63 times the volume of Earth, remained suspended silently in the night sky throughout the vast majority of human civilization's history, awaiting an era of technological maturity and intellectual liberation to be unveiled. Its concealment was not accidental, but an inevitable outcome of the combined constraints of human sensory limits and cognitive frameworks. The turning point in history first arrived in 1612. Galileo Galilei, the father of modern observational astronomy, aimed his hand-modified telescope at the starry sky. Though its magnification was modest, it revealed celestial details previously unseen. During systematic observations of Jupiter's moons, his notes unexpectedly recorded an inconspicuous celestial body, located in Pisces near the ecliptic. Galileo faithfully charted its position in his notes, and marked it as a star. He even observed this target again, during consecutive nights of subsequent observation, and recorded an extremely subtle shift in its position. Yet this discovery, capable of rewriting the history of astronomy, was overlooked by Galileo. He was then fully engrossed in his fierce debate with the Church over the heliocentric theory. His scientific focus remained firmly on validating the Copernican system. Jupiter and its moons, serving as a perfect miniature model of our solar system, consumed his entire attention. That faint point of light in the direction of Pisces appeared to him merely as another star awaiting classification. Even more regrettably, during his third observation, likely due to poor weather or telescope disturbances, his notes became indistinct. Subsequently, he seemed to lose all interest in this target, never conducting any follow-up observations. Today, reviewing Galileo's observation manuscripts and reconstructing the night sky of that day using modern astronomical software, we can definitively confirm that what he observed was Uranus. The minute movement he recorded, was precisely evidence of Uranus's slow progress along its vast orbit. Had Galileo recognized the significance of this movement at the time, if he had spared the energy to track this suspicious stellar point, the history of Uranus's discovery would have been advanced by nearly 170 years. The roster of the planetary family would have been entirely rewritten. Yet history knows no ifs. Galileo's misunderstanding became a classic missed opportunity in scientific history. Profoundly reveals a truth. Scientific discovery relies not only on advanced tools and keen observation, but also on a prepared mind and the correct theoretical framework to guide the direction. In an era that did not anticipate planets beyond Saturn, even the greatest scientists might mistake a new world for an ordinary star. This overlooked speck of light would continue its solitary, sideways roll through the cosmos, awaiting a discoverer more attuned to its true worth. And this wait stretched into yet another century. To grasp Uranus's peculiarity, one must first comprehend its suffocating remoteness. This pale blue planet orbits at an average distance of 2.9 billion kilometers from the Sun. This figure alone feels cold and abstract. We need more intuitive metaphors to sense this cosmic scale solitude. Imagine the 150 million kilometer distance between Earth and the Sun as one astronomical unit. Uranus lies 19.2 astronomical units beyond this, deep in the cosmos. If we shrink the solar system to the size of a football field, with the Sun at the center and Earth just 1.7 meters from it, Uranus would wander alone 32 meters away. That would be near the edge of the field, in a frigid zone scarcely graced by sunlight. This immense distance brings a most direct physical consequence. Sunlight here grows feeble and faint, reduced almost to the glow of an ordinary star. On Earth, the Sun is a dazzling, blindingly bright light source. Yet in Uranus's sky, it appears merely as an exceptionally bright speck. Its apparent diameter measures less than 1/40th of the Sun's size as seen from Earth. By the time its light and heat reach Uranus, they have diminished to a mere 0.25% of what Earth receives. It's akin to moving a stove capable of warming an entire room hundreds of meters away. The warmth it provides becomes negligible, scarcely enough to dispel the chill emanating from the depths of space. This profound remoteness finds its most striking expression in its despairingly long orbital period. Uranus requires a full 84 Earth years to complete a single revolution around the Sun. This means a child born on Uranus, even if living to what would be considered a ripe old age by Earth standards, would witness fewer than one complete Uranian year cycle in their lifetime. On Earth, the cyclical passage of seasons is a familiar year-to-year rhythm. Spring planting, summer cultivation, autumn harvest, and winter storage form the fundamental cadence of our lives. Yet on Uranus, time flows on an entirely different scale. If you were to celebrate the new year in Uranus's northern hemisphere, the next time you would witness spring's arrival would be 42 Earth years later. This disparity in temporal perception is sufficient to shatter any Earth-based life form's cognitive framework. Even more thought-provoking is Uranus' remarkably low orbital eccentricity. This means its orbit is nearly a perfect circle. Unlike the elliptical orbits of Mars or Jupiter, with distinct perihelion and aphelion points, Uranus' distance from the Sun varies very little throughout its entire revolution. It remains perpetually stationed in that frigid expanse of space, with no seasonal variations in proximity to offer even slight respite from its eternal frozen fate. This orbital stability further reinforces its image of isolation. It resembles not a wanderer periodically drawing near and receding from the Sun, but rather a frozen fortress anchored at a fixed position on the solar system's periphery, cold, constant, and eternally maintaining its distance. When we gaze upon the night sky, we see not merely the present-day Uranus, but a historical light and shadow spanning decades. Because the speed of light is finite, 300,000 kilometers per second, the light we see from Earth is actually emitted by Uranus 2 hours and 40 minutes prior. Every observation we make is a retrospective glimpse into the past. This temporal dislocation creates an insurmountable historical veil between us and the planet. This remoteness is not merely spatial, but temporal and perceptual. It fundamentally shapes Uranus's physical essence as a cold, lonely world, and dictates the immense technological challenges humanity faces in exploring it. Our probes require nearly a decade of journey to reach it, and the signals we receive are so faint they demand massive antenna arrays to capture. All this stems from the chasm carved by those 2.9 billion kilometers. This chasm allowed Uranus to remain hidden throughout most of human history, and has kept it shrouded in mystery and aloofness even after our discovery. Understanding this remoteness is the first step to comprehending Uranus's peculiar characteristics. For it is precisely the extreme cold and faint light brought by this distance that together set the stage for all the bizarre phenomena on this icy giant. Nearly 2 centuries passed after Galileo's misunderstanding. Humanity's understanding of Uranus remained confined to a vague point of light. We knew it was a planet, yet remained utterly ignorant of its true form. It wasn't until the latter half of the 20th century that a once-in-a-millennium opportunity arose. The planets aligned in a rare geometric sequence, allowing a probe to harness the gravitational slingshot effect and sequentially visit 4 giant planets, completing the monumental Grand Tour mission. This was the Voyager 2 mission, an epic voyage destined for the annals of history. Launched in 1977, after soaring past the wonders of Jupiter and Saturn, it turned its gaze toward the deep blue planet in the solar system's far reaches in January 1986. The scientific community viewed this flyby with both anticipation and trepidation, for Uranus was the first ice giant ever explored up close by humankind. We had almost no concept of the world it would reveal. Voyager 2 journeyed like a solitary pilgrim through the vast cosmos for nearly 9 years, covering over 3 billion kilometers, before finally reaching its closest approach to Uranus on January 24, 1986, at a distance of approximately 81,500 kilometers from its cloud tops. For this fleeting encounter, the ground team faced immense technical challenges. At such a great distance, sunlight was as faint as twilight. The spacecraft's cameras required long exposures to capture clear images. Signals traveling at the speed of light took 2.5 hours to reach Earth. A single misstep in command could have doomed the mission. Yet Voyager 2 flawlessly executed its mission. Within the precious window of hours before and after the flyby, it captured thousands of photographs and gathered vast amounts of magnetic field, particle, and atmospheric data. When this data finally crossed the vast expanse of space to reach scientists, it brought not the joy of resolution, but a seismic scientific shock. The very first images delivered a stunning revelation. The smooth, deep blue disk seen through telescopes had vanished. In its place was a nearly featureless, pale blue sphere. Uranus' visible cloud layers appeared unusually calm, lacking the vibrant stripes and violent storms seen on Jupiter and Saturn. It resembled a perfect, lifeless billiard ball. This visual monotony hinted at peculiar internal structures. Its upper atmosphere might be shrouded in thick methane haze, concealing any weather activity in lower layers. Yet a deeper shock came from measurements of its magnetic field. Earth, Jupiter, and Saturn's magnetic fields align roughly with their rotational axes. But Voyager 2 discovered Uranus's magnetic field is a massive outlier. Its magnetic field strength is about 50 times that of Earth's. But most perplexing is that its magnetic axis does not pass through the planet's center. Instead, It is tilted at an angle of about 60 degrees relative to the planet's core. Moreover, it forms a massive angle of nearly 60 degrees with its extremely tilted rotational axis. This implies Uranus' magnetic field behaves like a magnet knocked askew and carelessly placed, violently tumbling and rolling through space. This discovery instantly invalidated all traditional planetary models. Scientists speculate this distorted field may originate from the planet's interior. Specifically, a conductive superocean of water, ammonia, and methane, rather than an iron core like Earth's. Subsequent observations of the rings presented new puzzles. Eclipse observations had previously indicated Uranus possessed a ring system, but Voyager 2 captured the first clear images of these structures. It confirmed Uranus possesses at least 11 narrow, faint ring bands. These rings primarily consist of dark, carbonaceous material ranging from meters to tens of meters in size. Their reflectivity is extremely low, as if coated in soot. The outermost epsilon ring exhibits complex structure. Invisible shepherd moons appear to constrain the ring material on either side, keeping it narrow and stable. Additionally, the probe unexpectedly discovered 10 new small celestial bodies, namely Uranus's new moons. Most of these moons are small, dark, and heavily cratered. Together with the ring system, they form a complex minor system. Finally, through precise measurements of the atmosphere and temperature, Voyager 2 confirmed Uranus as the coldest planet in the solar system. Even on the sunlit hemisphere, the cloud tops reach a frigid -214 degrees Celsius. This confirms the planet appears to lack significant internal heat sources. Unlike Jupiter, Saturn, or even Neptune beyond, it does not radiate excess energy outward. This renders Uranus a thoroughly frozen, nearly inert world. Voyager 2's flyby was like a flash of lightning that momentarily illuminated this dim, icy giant. Yet this light vanished as quickly as it appeared, leaving behind more mysteries than answers. Why does this seemingly tranquil, frozen world possess such a warped magnetic field? How does its lack of internal heat influence global climate? In what physical state does that super-deep ocean of ice truly exist? These questions continue to challenge planetary scientists worldwide. This epic flyby completely rewrote astronomy textbooks. It did not end the discussion about Uranus. Instead, it ushered in a new, more complex era of exploration. When we discuss planetary rotation, the image of a spinning top often comes to mind. Whether it's our Earth, the brilliant Venus, or even the massive Jupiter and Saturn, they all maintain a largely upright orientation as they orbit. The angle between their rotational axis and the perpendicular to their orbital plane is small. Earth has a moderate tilt of 23.5 degrees. This gives us distinct seasons. Yet Uranus shatters this norm entirely. It stands as a true oddity in our solar system, a planet utterly misaligned. Its rotational axis isn't tilted by a slight angle, but by a staggering 98 degrees. What does this number signify? It means Uranus's axis lies nearly flat against its orbital plane. It resembles not a spinning top, but a bowling ball rolling sideways, or a giant wheel tumbling along its orbit. In a sense, it isn't rotating but tumbling sideways in its orbit. This peculiar posture creates an extraordinarily bizarre spectacle. At some point during its 84-year orbital cycle, its north pole points almost directly at the Sun. Then, after roughly half an orbital cycle, about 42 years, the South Pole takes its turn pointing straight at the Sun. Imagine this. On Earth, we can never witness the Sun directly overhead at the poles. But on Uranus, when the North Pole faces the Sun appears suspended directly above the North Pole, never setting. Meanwhile, at the equator, the Sun remains perpetually low on the horizon. This method of rotation is an unprecedented spectacle in astronomy. To grasp this more intuitively, let's conduct a simple physical simulation. Take a basketball to represent the sun. At a distance, tie an orange to a thin string. Have the orange orbit the basketball in a circular motion. This simulates the revolution. Now comes the crucial rotation. Spin the orange upright. This mimics Earth's rotation. Then tilt the orange nearly flat and spin it horizontally. This represents Uranus. You'll observe that when the Earth model spins upright, its north and south poles alternately face outward into space. But when the Uranus model spins horizontally, at two opposite points along its orbital path, its poles directly face the central sun. This motion pattern directly causes its extreme seasonal cycles. Before proceeding, we must correct a common visual misconception. Many imagine Uranus lying down as it orbits, like a bowling ball rolling down a circular lane. Yet a more accurate description is that it resembles a toppled sphere spinning rapidly, tumbling sideways along its orbit. Its equatorial plane tilts a staggering 97.8 degrees, almost a right angle. Thus, its seasonal changes defy any familiar pattern. So what force could have so thoroughly overturned a planet 63 times larger than Earth? The most widely accepted scientific hypothesis points to an ancient cosmic collision. Approximately 4 billion years ago, during the early formation of the solar system, interplanetary space teemed with primordial planets and debris. Through supercomputer simulations, astronomers speculate that a protoplanet, possibly 1 to 2 times the mass of Earth, collided head-on with the young Uranus at an apocalyptic angle and velocity. This impact likely struck obliquely rather than directly at the core. Enormous angular momentum was injected into the Uranus system, as if an invisible giant hand had violently shoved the giant planet, completely overturning its original rotational state. This catastrophic collision not only altered its rotational axis, but may have profoundly impacted its internal structure. One theory suggests the immense energy released by the impact may have vaporized or ejected substantial quantities of Uranus's primordial light elements. This could explain why the hydrogen-to-helium ratio in its atmosphere is significantly lower compared to Jupiter and Saturn. It is also possible that this collision event laid the groundwork for Uranus's twisted and peculiar magnetic field. The entire history of this planet appears defined by that ancient impact. It was transformed from a standard gas giant, possibly Jupiter-like, into the peculiar ice giant we observe today, a celestial body with an unusual orientation and unique interior. Its horizontal tilt was not a voluntary choice, but an eternal scar from a violent cosmic event. When we gaze through telescopes at that pale blue sideways sphere, we see not merely a planet, but a violent chapter from the early solar system, preserved within time and ice. A cosmic tale of collision and reshaping. This is Uranus's most fundamental paradox. Its seemingly tranquil, languid posture actually etches one of the solar system's most violent genesis moments. Uranus's 98-degree axial tilt is not merely an abstract astronomical figure. It directly spawned the most extreme, most frenzied climate rhythm in the solar system, a seasonal cycle stretching time to near-eternal scales. Within this cycle, traditional latitude-based climate zones are utterly overturned, replaced by an extreme alternation centered on the poles. Imagine standing at Uranus's North Pole. Here, the sun does not rise in the east or set in the west. Instead, like an eternal searchlight, firmly suspended directly overhead. It neither descends nor shifts, merely tracing minute circular paths across the sky. This is Uranus's polar summer, a perpetual daylight lasting 42 Earth years. What does 42 years signify? It signifies a child's journey from infancy to middle age. It signifies half of modern human civilization's history. It signifies the beginning and end of a major global war on Earth. At Uranus's north pole, the sun bakes the same frozen landscape without shifting. The thermal effect of such prolonged illumination is slow and cumulative. Though sunlight here grows faint as twilight, under half a century of focused radiation, energy steadily accumulates. This causes the directly sunlit polar region to reach temperatures abnormally higher than the obliquely lit equatorial zones. This represents a thermodynamic paradox utterly defying our terrestrial experience. In our familiar world, the equator is perpetually the hottest region. Yet on Uranus, one pole becomes the temporary thermal center. While the North Pole basks in its 42-year-long endless daylight, the South Pole plunges into an equally prolonged 42-year absolute darkness. This is not the polar night with dawn and dusk we know on Earth's poles, but a pure darkness approaching the cosmic background. The sun vanishes entirely below the horizon. No atmospheric scattering offers even a glimmer of comfort. Only distant stars and the occasional passing sibling moon bear witness to this forgotten, frozen realm. Here, temperature dissipates unimpeded, plunging toward cosmic frigidity near -224 degrees Celsius. The atmosphere across the entire hemisphere nearly ceases macroscopic motion, as if time itself has frozen. Yet the climax of this cosmic drama lies not in stillness, but in the suffocatingly long seasonal transition. Due to Uranus' nearly circular orbit, its seasonal shifts are driven primarily by angle of illumination, not distance. From the polar solstice point to the equatorial vernal or autumnal equinox, it takes a quarter of its orbital period, 21 Earth years, to traverse this path. These 21 years are not an instantaneous switch, but a gradual transition so slow it's nearly imperceptible. From its fixed point above the polar region, the sun begins tracing ever-widening spiral paths, drifting slowly toward the equator day after day, year after year. This process unfolds so slowly that within a human lifetime, the change remains virtually invisible to the naked eye, as if the cosmic clock spring had been deliberately slowed here. When the sun finally labors into position above the equator, Uranus welcomes its equinox. At this moment, the entire planet enters a brief and peculiar phase. Sunlight illuminates both hemispheres relatively evenly. Yet this astronomical equilibrium is fleeting. The sun continues its unstoppable journey, advancing toward the opposite pole, commencing another 42-year cycle of polar day. What effects do these extreme seasons exert on Uranus' climate? We can only speculate through limited probe data and theoretical models. During Voyager 2's 1986 flyby, Uranus' south pole was oriented toward the sun near the solstice. The probe detected an unusually bright region in its southern polar cap, termed the bright polar cap. This likely resulted from solar ultraviolet radiation, altering the composition of methane haze in the polar upper atmosphere, and increasing its albedo. When the Hubble Space Telescope observed Uranus again in the early 21st century, the planet had moved near the equinoctial point. At this time, the previously dark northern hemisphere began receiving sunlight. Scientists were surprised to find intense storm activity in the northern hemisphere, with cloud layers becoming active and variable. This seemed to indicate that this frozen world was not lifeless. When sunlight first illuminated the long dormant hemisphere, it triggered a violent response in its atmosphere. The source of this energy remains a mystery, as sunlight itself is too faint. This suggests that beneath Uranus's icy exterior, a more complex atmospheric energy storage and release mechanism may be concealed. This extreme 42-year illumination cycle not only impacts the atmosphere but must profoundly influence its internal structure. That global superocean of ice, under the alternating effects of polar heating and freezing, might trigger a slow, global-scale circulation. Could the peculiar behavior of its magnetic field also relate to this periodic redistribution of heat? The answers to all these questions lie hidden within this cosmic-scale chaotic cycle, awaiting revelation by a dedicated probe in the future. As we marvel at Earth's changing seasons of spring, summer, autumn, and winter, spare a thought for that blue planet tumbling sideways in deep space. With an 84-year life cycle, it stages a grand drama of light and darkness, of heat and cold. Each act of this drama spans a human middle age, its rhythm so slow, its shifts so extreme, enough to make any transient life form feel its own insignificance and impermanence. This is the cosmic truth Uranus tells us through its very existence. Diversity exists not only in life forms but also in the most fundamental laws of nature. In the boundless universe, even a seemingly ordinary concept like seasons can be interpreted as a near-eternal madness. On our familiar Earth, heat distribution follows a simple, intuitive law. The equatorial regions, perpetually under direct solar radiation, receive the most solar energy and are thus the hottest. As latitude increases toward the poles, the angle of sunlight becomes increasingly oblique. The energy received per unit area consequently diminishes, and temperatures gradually decrease. This fundamental thermodynamic principle, determined by the angle of incidence, shapes all atmospheric circulation and climate patterns on our planet. Yet, when astronomers turned their gaze toward Uranus, they observed a phenomenon that utterly overturned this understanding. During summer, the polar regions of this ice giant actually exhibit significantly higher temperatures than its equatorial zones. This represents a cosmic-scale thermodynamic paradox, a peculiar phenomenon never observed on any other planet in our solar system. To understand the root of this anomaly, we must return to Uranus's signature 98-degree axial tilt. It is precisely this extreme sideways posture, combined with its suffocatingly long orbital period, that jointly orchestrates this thermodynamic inversion. Imagine Uranus at its northern solstice. Its north pole perpetually faces the sun. For a staggering 42 Earth years, sunlight strikes nearly perpendicular to the North Pole, though its intensity is merely 0.2% of Earth's. As faint as Earth's twilight, this illumination is constant and uninterrupted. No day-night cycle disrupts the accumulation of heat. It's akin to a low-wattage electric blanket that never switches off, baking the polar region for extended periods. Heat slowly yet steadily permeates and accumulates within the atmosphere and surface layers. Meanwhile, what illumination conditions prevail at Uranus's equator? During the polar summer solstice, the equatorial plane lies nearly parallel to the sun's rays. Sunlight can only graze the equatorial region at an extremely oblique angle. This oblique incidence means the solar energy received per unit area is negligible. More significantly, due to Uranus's rapid rotation, its equatorial region experiences a normal day-night cycle approximately every 17 hours, Uranian days. The brief heat absorbed during daylight is quickly dissipated during the long night. There is insufficient time for effective heat accumulation. This fundamental difference in illumination patterns is the first key factor explaining why polar regions are warmer than the equator. However, this alone cannot fully account for the observed temperature disparity. Another crucial factor lies in Uranus's own physical state. Data from Voyager 2 confirmed that Uranus's interior is exceptionally cold. Unlike Jupiter and Saturn, it lacks a powerful internal heat source, capable of transferring vast amounts of energy from the planet's depths to its atmosphere. The absence of an internal heat source means Uranus' atmospheric thermodynamics are almost entirely driven by solar input. resulting in a relatively simple and sluggish atmospheric circulation system. On Earth, a powerful internal heat source combined with rapid rotation fuels complex and vigorous atmospheric circulation. This circulation efficiently transports excess equatorial heat to the polar regions, thereby balancing global temperature differences. On Uranus, however, this large-scale heat transfer is extremely inefficient. Polar regions, continuously baked by the sun for decades, struggle to effectively diffuse their heat to the equator through slow atmospheric movements. Heat appears trapped in the polar regions, creating localized high-temperature centers. Additionally, scientists speculate that the abundant methane in Uranus' atmosphere plays a crucial role in this anomalous phenomenon. In the upper polar atmosphere, continuously exposed to ultraviolet radiation, special photochemical reactions may occur. Methane molecules are broken down and may repolymerize into more complex hydrocarbons. These substances form a layer of smog covering the polar regions. They may absorb more solar radiation or alter the thermal structure of the atmosphere, thereby further intensifying polar warming. Meanwhile, the other pole, shrouded in perpetual night, continues to cool due to the absence of such processes. Ultimately, the convergence of all these factors, decades of sustained energy input, inefficient global heat redistribution mechanisms, and potentially unique polar photochemical processes, collectively fostered this singular thermodynamic phenomenon on Uranus. It reveals a profound truth. Planetary climate is an extraordinarily complex system. When certain parameters are pushed to extremes, such as Uranus's extreme axial tilt and prolonged seasons, the resulting phenomena can completely overturn our Earth-based common sense. Studying Uranus's paradox not only helps us understand this icy giant at the solar system's edge, but also provides crucial insights for interpreting the abundance of similarly side-lying planets. Among exoplanets, across the vast cosmos, countless climate patterns diverging from Earth's must exist, and Uranus stands as a precious natural laboratory right beside us. Its very existence, constantly reminding us that the universe's diversity and complexity far surpass our limited imagination. Uranus holds the record for the lowest temperature among the solar system's planets. On its hemisphere, shrouded in a prolonged polar night, temperatures can plummet to -224 degrees Celsius. This figure represents an extreme cold beyond human everyday experience. To grasp the magnitude of this cold, we must first understand the concept of absolute zero. Absolute zero is -273.15 degrees Celsius, the thermodynamic lower limit of temperature. It signifies the complete cessation of molecular thermal motion. Uranus's -224 degrees Celsius lies a mere 49 degrees from this theoretical limit, approaching the coldest state conceivable in nature. In such an environment, the properties of matter undergo fundamental changes. The primary components of Earth's atmosphere would solidify here. Oxygen would condense into pale blue solid particles. Nitrogen would form white ice crystals. Even the lightest hydrogen would transform into metallic hydrogen. This extreme cold brings not only changes in physical states, but also a world where molecular activity nearly ceases. Sound relies on the vibration of molecules in a medium to propagate. Yet deep within Uranus' atmosphere, molecular motion slows to such an extent that sound waves can scarcely propagate effectively. This realm approaches physical silence. This frigidness also impacts light propagation. As the atmosphere is shrouded in a haze of methane ice crystals, light undergoes complex scattering among these icy particles. This may partly explain Uranus' uniform pale blue hue. This blue differs from the azure of Earth's oceans, resembling instead a flawless sapphire, emitting a cold, pure radiance. Notably, this lowest temperature record was measured on Uranus's night hemisphere, particularly in polar regions enduring prolonged polar night. Here, sunlight has been absent for over 40 consecutive years. Heat continuously escapes into space, and Uranus's interior lacks significant thermal sources to replenish it, enabling temperatures to plummet to such extreme levels. In contrast, the more distant Neptune, though receiving less solar radiation, possesses an active internal heat source, resulting in surface temperatures several dozen degrees higher than Uranus. This fact renders Uranus's extreme cold even more exceptional. Such an environment of extreme low temperatures poses challenges to our understanding of material states. In terrestrial laboratories, creating environments approaching -224 degrees Celsius requires highly complex refrigeration systems and substantial energy consumption. Yet on Uranus, such temperatures are the planetary norm. This provides a natural laboratory for studying physical and chemical processes under extreme conditions. Images transmitted by Voyager 2 reveal Uranus's unsettling tranquility. Its pale blue sphere shows almost no discernible features, compared to Jupiter's ceaseless, colorful storms, or Saturn's regularly spaced cloud bands. Uranus appears unusually silent. This visual calm stems from its atmosphere's unique state at extreme cold. At such low temperatures, the average thermal motion of atmospheric molecules slows significantly, greatly weakening vertical convection. Without strong updrafts and downdrafts, distinct cloud formations cannot develop, making the entire planetary surface appear as still as water. Yet this calm is merely superficial. More precise observations reveal the mystery. When the Hubble Space Telescope turned its gaze toward Uranus, scientists were astonished to discover that within specific spectral bands, the planet's atmosphere is actually teeming with activity. Dozens of cloud formations can be observed, engaged in continuous convective activity within these layers. These cloud masses, likely composed of methane ice crystals, appear and disappear intermittently, indicating energy exchange within Uranus' atmosphere. Particularly striking is the phenomenon during seasonal transitions, when sunlight first illuminates the hemisphere emerging from a prolonged night. Uranus' atmosphere displays astonishing vitality. Scientists have observed massive storm systems, exceeding the size of North America. These storms can persist for months or even years, revealing the hidden energy within this frozen world. So what fuels these atmospheric activities? With such faint solar radiation and virtually no internal heat source, this puzzle has long perplexed planetary scientists. One theory suggests that Uranus' atmosphere may harbor a unique mechanism for storing and releasing energy. During the polar day, the atmosphere slowly absorbs and stores solar energy. Though this process is extremely gradual, over a 42-year period, it accumulates substantial energy. When seasonal transitions begin and atmospheric structures shift, this stored energy may be released, driving storm and circulation systems. Another possible explanation is that despite Uranus's overall frigid interior, localized temperature variations may still exist. Though these differences are small, under specific conditions, they could be sufficient to drive atmospheric motion. Much like a pot of nearly still cold water, even a slight temperature gradient can generate slow convection. Recent research also indicates certain components in Uranus's atmosphere may undergo phase transitions under specific conditions, releasing latent heat to supply additional energy for atmospheric motion. These processes collectively enable this seemingly frozen world to maintain faint yet persistent atmospheric activity. When we gaze upon Uranus's tranquil blue exterior, we should recognize that beneath this eternal stillness lies the pulsation of the cosmos. The operational principles of this world continue to challenge our existing understanding, awaiting future probes to reveal them. To understand why Uranus tilts on its side at such an unusual angle, we must return to the chaotic era 4.6 billion years ago when the solar system was born. Back then, the solar system was not the orderly place it is today, but a violent, chaotic cosmic battlefield. Countless protoplanets and interstellar debris collided wildly within the newborn sun's gravitational field. This was a Genesis era where creation and destruction occurred simultaneously. In the early stages of solar system formation, a vast protoplanetary disk encircled the newborn sun. This rotating disk of gas and dust served as the cradle for planetary birth. Within this disk, tiny dust particles began colliding and coalescing, growing like snowballs from millimeter-sized grains to kilometer-sized planetesimals, to moon-sized protoplanets. This process spanned millions of years. Yet this growth was far from peaceful. Under gravitational forces, the orbits of these diverse celestial bodies intersected, inevitably leading to frequent collisions. Some collisions were gentle mergers, accelerating growth, but more were devastating impacts at extreme relative speeds. The inner solar system was particularly crowded. Potentially dozens of protoplanets, ranging from lunar to Martian scale, coexisted, chasing each other along chaotic orbits. This cosmic scale game of pinball persisted for roughly 100 million years, a period known as the Late Heavy Bombardment. Evidence of this era remains preserved on the lunar surface, where densely clustered impact craters stand as the most compelling testimony. Mercury's cratered surface, and the striking differences between Mars' northern and southern hemispheres may both be products of this violent era. Even Earth was not spared. Scientists believe it was during this period that a Mars-sized protoplanet named Theia collided with the primordial Earth. The debris from this impact eventually coalesced to form our moon. This hypothesis, known as the giant impact theory, not only explains the moon's origin, but also confirms that massive collisions capable of altering planetary destinies indeed occurred in the early solar system. Against this chaotic backdrop, conditions in the outer solar system were even more complex. During their formation, the young Jupiter and Saturn may have undergone orbital migration. Their immense gravitational pull acted like cosmic bulldozers, stirring up the distribution of material throughout the planetary disk, possibly swapping the positions of Neptune and Uranus, while flinging Kuiper belt objects into the far reaches. This theory, known as the Nice model, paints a picture far more turbulent than that of the inner solar system. In this survival of the fittest cosmic environment, the newly formed Uranus remained in a relatively unstable state. Its orbit may have resonated or intersected with other protoplanets, much like a toddler learning to walk. In a crowded room filled with obstacles, a constant risk of being knocked over. Around Uranus at that time, several Earth-mass primordial bodies may have been orbiting in similar paths. Gravitational interactions gradually pushed some of these bodies off course, ultimately leading to inevitable collisions. The energy released in these collisions was staggering. A single major impact could unleash energy, equivalent to trillions of atomic bombs detonating simultaneously, enough to melt an entire planetary surface, alter its rotational state, or even completely reshape its internal structure. In such an environment, It was not uncommon for planets to have their rotational axes knocked askew. Venus's slow, retrograde rotation near an inverted state may stem from a massive collision. Earth's 23.5-degree axial tilt likely solidified during this era, yet Uranus endured collisions more extreme and violent. Understanding this chaotic genesis period is crucial for comprehending our solar system. It reveals that the orderly solar system we observe today evolved from profound disorder. Each collision and gravitational disturbance shaped the final form of the planets. Uranus's 98-degree tilt is not an innate anomaly, but an eternal imprint of that violent epoch, a testament to a cosmic tale of survival and destruction. One of the most captivating achievements in modern astrophysics is the reconstruction, via supercomputer simulations, of that ancient collision that altered Uranus's destiny. These simulations process billions of computational particles, each adhering to precise physical laws, recreating that breathtaking moment from 4 billion years ago in virtual spacetime. Simulation results reveal the impact scenario most consistent with Uranus's current state. A protoplanet roughly twice Earth's mass struck the still-forming Uranus at a relatively moderate angle of approximately 45 degrees. The scale of this collision surpassed any catastrophe imaginable. The energy released in the instant of impact equaled detonating 1 billion tons of TNT, billions of times greater than the asteroid strike that wiped out the dinosaurs. The impactor hurtled toward primordial Uranus at tens of kilometers per second, first encountering its relatively thin atmosphere. Yet this gaseous shield proved utterly meaningless against such immense kinetic energy. Torn apart as easily as a bullet piercing butter, the impactor then penetrated Uranus's primordial crust. Enormous pressure instantly vaporized material in the impact zone, forming a molten abyss thousands of kilometers deep. The shockwave generated by the impact propagated through the planet's interior at near light speed, completely disrupting its originally layered structure. The iron-nickel core was violently compressed and deformed by the impact energy. The silicate mantle and icy outer layers became thoroughly mixed, forming a homogeneous fluid sphere. The most critical change occurred during angular momentum transfer. Due to the oblique impact angle, enormous angular momentum was injected into the Uranus system. It was as if an invisible cosmic hand had violently shoved the planet, forcing it to begin rotating at a completely new angle. Most of the debris ejected by the impact was recaptured by Uranus's gravity, forming a brief ring system around the planet. Over millions of subsequent years, this material gradually settled, redistributing itself across the planet's surface and interior, altering Uranus's overall composition and structure. A small fraction of material escaped Uranus's gravity at extreme velocities, vanishing forever into interstellar space. Supercomputer simulations also revealed another crucial detail. This impact likely occurred late in Uranus's formation process, when the planet was largely shaped but its internal structure had not yet fully solidified. This timing was critical. Had the impact occurred too early, the planet, not yet fully formed, might have been shattered completely. Had it occurred too late, the planet's interior would have been too solid to undergo such enduring internal changes. It was precisely this perfect timing that allowed the impact to both alter the rotational axis and reshape the internal structure without destroying the planet. Simulations also indicate the composition of the impactor was critical. An icy impactor explains why Uranus contains such a high proportion of water ice, ammonia ice and methane ice mixtures. These volatiles were partially preserved during the impact and uniformly mixed throughout the planet's interior, forming the unique global ice ocean we detect today. This simulation not only explains Uranus's peculiar rotational axis, but also successfully predicts many of its other characteristics, including its unusually cold interior, warped magnetic field, and relatively uniform atmospheric composition. These predictions show strong agreement with subsequent observational data, providing robust support for the impact hypothesis. However, this theory still faces challenges, such as why Uranus's satellite system also exhibits orbital alignment consistent with the rotational axis. This requires either a post-impact satellite formation process, capable of inheriting the planet's angular momentum characteristics, or satellites reformed from debris following the impact. Scientists are currently developing more precise models to explain every detail within this complex system. Each new simulation run brings us closer to the truth that altered Uranus's destiny. The immediate consequence of this cataclysmic impact was a permanent alteration of Uranus's rotational state. The massive injection of angular momentum caused the planet's rotational axis to tilt nearly 90 degrees, shifting from a relatively upright orientation to a nearly horizontal position. The heat generated by the impact melted most of the planet's interior, completely disrupting and reorganizing its previously layered structure. Heavy elements like iron and nickel sank toward the center, forming a new core. Lighter icy materials and water rose to form an extensive icy mantle. This process of internal restructuring lasted millions of years, ultimately creating the layered structure we detect today. A small, dense rocky core enveloped by a global superocean of ice. The impact may also have altered the planet's thermal evolution history, resulting in Uranus's unusually cold interior with no significant heat source. This collision not only shaped Uranus's external appearance, but also determined its intrinsic nature, making it the unique ice giant in the solar system. Beneath the ice giant's deep blue exterior lies a solid core strikingly similar to Earth's. This secret, deeply buried at the planet's core, holds the key to understanding Uranus's true nature. Precise calculations by modern astronomy reveal Uranus possesses a solid core roughly half the diameter of Earth, with a mass nearly equivalent to the entire Earth. This core is primarily composed of iron and silicate minerals, sharing significant similarities in composition and structure with Earth's inner core. However, the environment surrounding this Earth-like core differs vastly from that of Earth. It does not float within molten lava, but lies buried beneath a vast ocean of super ice, enduring unimaginable pressure. Scientists have gradually unveiled this hidden secret through multiple indirect methods. The most crucial clue came from precise measurements of Uranus' gravitational field. During its 1986 flyby, the Voyager 2 probe recorded minute variations in Uranus' gravitational field. These data, akin to the planet's fingerprint, revealed detailed information about its internal mass distribution. Through complex mathematical models and computer inversions, scientists reconstructed a density distribution map of the planet's interior. The results showed a highly dense spherical region at Uranus' core, with a density reaching approximately 9 grams per cubic centimeter. This closely matches the density characteristics of Earth's core. Another key piece of evidence comes from studies of Uranus's magnetic field. This peculiar, tilted and offset magnetic field suggests a unique mechanism for its generation. Earth's magnetic field is primarily generated by electric currents in its liquid outer core. Uranus's magnetic field, however, may originate from the region surrounding its core, a conductive superice ocean composed of water, ammonia, and methane. Yet certain features of the magnetic field still point to the existence of a solid core with some conductivity. This core may be partially molten, or exist in a special state under extreme high temperatures and pressures. Core temperatures are estimated to reach 5,000 degrees Celsius, comparable to Earth's inner core. However, immense external pressure, estimated to be over twice that at Earth's center, forces iron and silicates to maintain unique crystalline structures. These extreme conditions are impossible to fully replicate in terrestrial laboratories. Regarding the core's formation, scientists propose two primary theories. One posits its natural formation through accretion. In the early solar system, iron and silicate particles first coalesced, forming the planet's primordial core. This core's gravity proved sufficiently strong to attract vast quantities of hydrogen and helium gases, along with diverse icy materials. The other theory suggests the current core structure resulted from a massive impact. The collision's energy may have melted the original core, causing heavy elements to resettle, with lighter elements rising to the surface, forming the layered structure observed today. Regardless of which theory prevails, the existence of this terrestrial core provides Uranus with the essential mass foundation to sustain its thick, dense atmosphere and complex internal structure. Core heat transfer also influences the planet's thermal evolution. Though Uranus' interior is exceptionally cold, heat from the core still radiates outward at an extremely slow pace. This sluggish thermal convection may play a crucial role in sustaining its peculiar tilted magnetic field. When contemplating Uranus, we should not be deceived by its icy exterior. Beneath layers of frozen ice beats a heart of the same origin as Earth's. This discovery reminds us that no matter how bizarre a celestial body may appear, its fundamental building blocks and governing physical laws are no different from those in our familiar world. This Earth-like core, hidden deep within the ice giant's center, is not merely an object of scientific study, but a bridge connecting us to the distant cosmos. By examining it, we not only uncover Uranus's past, but also explore universal principles of planetary formation. This Earth-sized inner core, through its silent existence, whispers to us of the solar system's formative era, a chaotic yet profoundly creative time. Enveloping Uranus' core lies a vast, boundless super-ice ocean. This ocean scale far exceeds the combined volume of all Earth's oceans. Its depth may reach tens of thousands of kilometers, spanning over 2/3 of the planet's radius. Yet this ocean is not the liquid water we know, but a special fluid composed of water, ammonia, and methane. Under extreme high-pressure, high-temperature conditions, the physical state of this super-ice ocean defies our everyday understanding. Under pressures at depths of thousands of kilometers, though temperatures may reach thousands of degrees Celsius, far exceeding water's critical point, these substances cannot evaporate freely as they do on Earth's surface. Enormous pressure compresses molecules tightly together, forming a state that is neither typical liquid nor typical solid, a supercritical fluid. This uniquely structured substance is termed by scientists as thermal ice or superionic ice. In this state, oxygen atoms within water molecules are locked within a crystal lattice, forming a structure akin to solid ice. Conversely, hydrogen atoms move freely through the lattice, as they would in a liquid. This creates a peculiar conductive fluid, capable of efficiently transmitting electrical current. This property may hold the key to explaining Uranus's peculiar and distorted magnetic field. The precise composition of the superice ocean remains a primary research focus. Current understanding suggests it consists primarily of water molecules, accounting for approximately 60% of the total volume, alongside significant proportions of ammonia and methane. Under extreme conditions, These components undergo complex chemical reactions and phase transitions. The presence of ammonia acts as a natural antifreeze, significantly lowering the mixture's freezing point, enabling the ocean to remain fluid across a broader temperature range. Methane plays an equally crucial role, not only as a primary contributor to Uranus's blue appearance, but also as a key player in the planet's internal heat cycle. Methane may exist as hydrates, or form complex inclusion structures with other components. These unique molecular configurations profoundly influence the physical and chemical properties of the entire icy ocean. The temperature distribution within this ocean is highly uneven, spanning an astonishing range, from nearly -200 degrees Celsius at the outer layers, to thousands of degrees Celsius near the core boundary. However, due to the extremely high-pressure environment, even in the hottest regions, matter maintains some form of ordered structural state. This peculiar phenomenon is almost unimaginable on Earth. Convection patterns within the superocean are also highly unusual. In Earth's oceans, thermal convection is primarily driven by density changes caused by temperature gradients. However, within Uranus's superocean, differences in composition likely play a more significant role. Variations in the proportions of different components across regions create density stratification, driving an extremely slow yet vast circulation system. This circulation may persist for millions of years. The viscosity of this ocean is also astonishing. Unlike Earth's water, it does not flow easily. Instead, it resembles a thick layer of hot ice cream, or some high-temperature glassy substance. This high viscosity characteristic makes energy transfer exceptionally slow. This may partially explain why Uranus's interior appears so cold, lacking significant heat sources. Regarding the origin of this superice ocean, two primary hypotheses exist within the scientific community. One posits that it formed naturally, through the direct accretion of massive icy planetesimals during Uranus formation. The other suggests it is a product of that massive impact, where the collision's energy melted the primordial ice layer, causing heavy elements to sink and light elements to rise, ultimately forming today's layered structure. This enigmatic superice ocean not only constitutes the core of Uranus's internal structure, but is likely the root cause of numerous observational phenomena. Its unique electromagnetic properties shape the planet's peculiar magnetic field. Its slow thermal convection patterns determine the planet's thermal evolutionary history. Its complex composition distribution influences material cycles within the atmosphere. When we gaze upon that faint blue speck in the night sky, we should recognize that beneath its serene exterior lies a dynamic and intricate inner world. The existence of this superocean not only makes Uranus unique within the solar system, but also provides the most direct reference sample for understanding the ice giant class of exoplanets. With future advances in exploration technology, we may gain deeper insights into this enigmatic ocean. Its waves, its circulation, its chemical composition will all reveal more secrets about planetary formation and the state of matter in the cosmos. This superocean hidden in deep space awaits humanity to explore every one of its mysteries. Uranus appears uniquely soft blue through telescopes. This color is no accident, but the precise result of its atmospheric composition interacting with its internal structure. Behind the planet's blue mantle lie intricate physical and chemical processes. First, we must understand the nature of visible light. The white light emitted by the sun actually encompasses the entire spectrum of colors. When these rays encounter a planetary atmosphere, light of specific wavelengths is absorbed, while other wavelengths are reflected or scattered, ultimately determining the planet's visible color. The most crucial coloring agent in Uranus' atmosphere is methane gas. Although hydrogen makes up over 80% of the atmosphere's volume, and both hydrogen and helium are colorless and transparent. It is methane, comprising only about 2%, that truly gives Uranus its blue appearance. These methane molecules possess unique absorption properties. They strongly absorb red and orange wavelengths of light, while remaining relatively transparent to blue and green wavelengths. This process acts like a cosmic scale filter. As sunlight passes through Uranus' atmosphere, the red portion is heavily absorbed, while blue light penetrates deeper, or is reflected back into space. Ultimately, the predominant light reaching our eyes is blue. This explains why Uranus appears such a uniform blue. However, methane alone cannot fully account for this unique hue. Scientists have observed that Uranus appears paler than Neptune, exhibiting a softer, bluish-green tint. This difference likely stems from two key factors. First, Uranus' atmosphere contains relatively lower methane concentrations. Second, its atmosphere is significantly calmer, lacking intense vertical motion. A haze composed of methane ice crystals may exist in Uranus's upper atmosphere. These minute ice crystals scatter light across all wavelengths, creating a frosted glass effect that blurs surface features, while lending the planet a softer, more uniform color. Evidence for this haze layer is supported by data from the Voyager 2 probe. Further research suggests Uranus's blue hue may also be linked to its internal superice ocean. Though we cannot directly observe this ocean, it indirectly influences the planet's color by affecting atmospheric composition. Methane trapped within the ocean may slowly seep into the atmosphere through geological processes, continuously replenishing atmospheric methane levels and maintaining the planet's blue exterior. Planetary scientists discovered through spectral analysis that Uranus's blue hue also contains faint green undertones. This suggests that beyond methane, other trace components may influence its color. Hydrocarbons like ethane and ethylene, though present in extremely low concentrations in the atmosphere, subtly alter the overall color balance. Compared to Neptune, Uranus exhibits a more uniform and gentle hue, reflecting its relatively calm atmospheric state. Neptune's intense atmospheric activity, driven by internal heat sources, results in its blue coloration featuring more prominent white cloud bands and dark spots. Uranus, lacking such internal energy, possesses a more stratified and stable atmosphere, naturally yielding a more uniform color. Seasonal changes also influence Uranus's blue appearance. During its 42-year-long polar day, constant sunlight may alter the chemical composition of the upper atmosphere, affecting the thickness and distribution of methane ice crystal haze, thereby subtly shifting the intensity of its blue hue. Though gradual, this variation has become detectable through decades of continuous observation. Notably, Uranus's blue hue is not static. When observed through filters of different wavelengths, this color exhibits significant variations. In the infrared spectrum, it appears nearly gray, while the ultraviolet spectrum reveals greater detail. These multi-wavelength observations provide invaluable clues for understanding its atmospheric structure. Understanding Uranus's color holds significance beyond aesthetics. It is crucial for studying its atmospheric composition and dynamics. By analyzing subtle shifts in its blue hue, scientists can infer atmospheric temperature, pressure, and composition distribution, and even detect seasonal climatic variations. This planet's blue mantle acts like a mirror, reflecting its internal structure and state. Each precise measurement of its color constitutes a vital sign check on this icy giant. As observational technology advances, we may uncover further secrets within this blue expanse. When we gaze upon that blue speck in the night sky, we see not merely reflected sunlight, but the outward manifestation of a complex physical and chemical system. This serene blue is both a scientific enigma and a display of cosmic beauty. It reminds us of nature's intricate and complex design, even on the most distant celestial bodies, where physical laws we can comprehend still prevail. When Voyager 2 approached Uranus in 1986, scientists anticipated encountering a world of near-stagnant calm. Based on prior ground-based observations, the ice giant's atmosphere appeared remarkably uniform, with scarcely any discernible features. All expected a visit to a tranquil planet. Yet when the probe began transmitting its first high-resolution images, the atmosphere in mission control shifted instantly. In the enhanced images, scientists were astonished to discover multiple bright cloud formations, moving at incredible speeds through Uranus' atmosphere. Precise measurements revealed one of the most prominent clouds traveling at 820 kilometers per hour. This surpassed the wind speed record of Earth's strongest hurricanes. As more data streamed in and detailed analysis unfolded, even more astonishing facts emerged. These high-speed winds were not confined to localized areas, but persisted on a planetary scale. Peak wind speeds were even measured at 900 kilometers per hour, equivalent to twice the cruising speed of a Boeing 747. Such velocity would be sufficient to circle the Earth in just a few hours. These storms are primarily composed of methane ice crystals. In Uranus' frigid atmosphere, methane condenses into bright, cloud-like structures that serve as visible markers for tracking atmospheric movements. The scale of these storms is equally staggering. Individual cloud masses often exceed the size of North America and can persist for weeks or even months. What puzzles scientists most is the source of these storms' energy. Uranus receives only 0.025% of the solar radiation Earth receives. Its interior is also confirmed to be exceptionally cold, lacking significant heat sources. According to traditional theories, this planet should possess a relatively calm atmospheric system. Yet the observed wind speeds rival those of the solar system's most active meteorological world. Further analysis revealed another puzzle. These high-speed wind currents align with the planet's rotation direction, yet exhibit significant speed variations across different latitudes. Equatorial regions show markedly lower wind speeds than mid-latitude zones. This wind distribution pattern differs entirely from other solar system planets, suggesting the uniqueness of Uranus' atmospheric circulation system. Probes also discovered these storms do not remain stationary at fixed altitudes, but instead form complex vertical structures between different atmospheric layers. Some cloud masses rise to the top of the troposphere, forming massive structures resembling thunderstorm clouds. Others remain in the middle and lower levels, moving along specific isobars, exhibiting multi-layered atmospheric motion characteristics. These observations have fundamentally transformed our understanding of the ice giants. Uranus is not a lifeless world. Beneath its serene blue exterior lies a terrifyingly violent force. This coexistence of tranquility and fury stands as one of the most captivating enigmas in planetary science. Voyager 2's discoveries ushered in a new era of research, compelling scientists to rethink the theoretical foundations of planetary atmospheric dynamics, particularly regarding how celestial bodies, devoid of significant internal or external heat sources. The answer to this question may revolutionize our understanding of planetary energy balance. This exploration also reminds us that the universe is always more complex and fascinating than we imagine. Even within our own solar system, countless unsolved mysteries remain. Each new discovery pushes the boundaries of science and ignites humanity's eternal desire to explore the unknown. Observations by the Hubble Space Telescope in the early 21st century revealed more persistent and violent phenomena within Uranus' atmosphere. As sunlight began illuminating the northern hemisphere after its prolonged polar night, the planet seemed to awaken from slumber, displaying breathtaking meteorological activity. In 2007, astronomers observed a colossal storm system, spanning an area equivalent to 2/3 of Earth's surface. This immense meteorological phenomenon persisted for a full 15 years, before gradually dissipating in 2022. Such longevity completely overturns Earth-based meteorological understanding. Even more astonishingly, these storm systems often appear in clusters, forming cloud belts stretching thousands of kilometers. Multiple bright cloud clusters observed in 2014 maintained active states for 5 consecutive years, orbiting the planet at constant speeds, while undergoing morphological changes, yet retaining stable core structures. This long-term stability indicates Uranus' atmospheric circulation possesses remarkable inertia. The energy scale of these long-lived storms also defies imagination. A single storm system releases energy equivalent to hundreds of times the total annual energy of all hurricanes on Earth. Multiple such storm systems may coexist simultaneously, collectively forming a global energy network that continuously reshapes Uranus' atmospheric landscape. Long-term monitoring data reveals these storm systems exhibit distinct cyclical patterns. Cloud activity in certain regions reoccurs every few decades, potentially linked to planetary-scale atmospheric oscillations, and suggesting a regular energy release mechanism within Uranus. The vertical structure of these storms is equally astonishing. Some cloud masses penetrate multiple atmospheric layers, extending from the deep convective zone all the way to the base of the stratosphere, forming three-dimensional structures hundreds of kilometers tall. This vertical scale dwarfs any storm system on Earth. Observations further reveal that these persistent storms profoundly influence Uranus's global climate. Acting like giant mixers, they promote heat and material exchange between different latitudes, alter the distribution of atmospheric chemical components, and may even influence subtle variations in the planet's magnetic field. Most perplexing of all is how these storms persist for decades, without apparent internal or external heat sources, forcing us to rethink fundamental principles of planetary atmospheric dynamics. Perhaps on ice giants like Uranus, there exist energy storage and conversion mechanisms that remain unknown to us. Faced with the immense energy demands of Uranus' atmospheric activity, scientists have proposed multiple possible explanations. No definitive conclusion has been reached to date. The most widely accepted hypothesis suggests this may be linked to gravitational wave energy transfer at the boundaries between fluid layers of differing densities within Uranus's interior. Large-scale gravitational waves may be generated. These oscillations can efficiently transport deep-seated energy to the atmosphere, much like internal waves in oceans can bring deep-sea energy to the surface. Another theory focuses on seasonal energy storage. During the 42-year-long polar day period, the atmosphere may act like a giant capacitor, storing solar energy. When seasons change, this stored energy is suddenly released, driving intense atmospheric circulation. This mechanism explains why storm activity is closely linked to seasonal shifts. Some scholars have also proposed the hypothesis of internal heat sources. Although Uranus's interior is exceptionally cold overall, localized radioactive element decay, or latent heat released during phase transitions, may exist, While these dispersed heat sources are individually small in scale, their combined total may be sufficient to sustain the observed atmospheric activity. The latest computer simulations reveal Alfvén waves may play a pivotal role. These specialized magneto-hydrodynamic waves can form within the conductive icy ocean and couple with the atmosphere through the magnetic field, injecting sustained energy into the upper atmosphere. Another theory suggests this could result from multiple mechanisms acting in concert: gravitational tidal forces, magnetic field energy dissipation, the inertial motion of the atmosphere itself. These processes combine, forming a self-sustaining energy cycle. Solving this energy puzzle is not only crucial for understanding Uranus, but will also aid our comprehension of similar planets in other solar systems. Each new set of observational data advances the progress of unraveling this mystery. The discovery of Uranus rings stands as one of the most dramatic serendipitous finds in astronomical history. On March 10, 1977, an international team of astronomers prepared to observe a rare celestial event, where Uranus would pass in front of a dim star named SAO 158687. This phenomenon, known as an occultation, would enable scientists to precisely measure Uranus' atmospheric properties and diameter. While the team conducted observations from the Kuiper Airborne Observatory in Australia and the Perth Observatory, an unexpected phenomenon occurred. Before the planet itself blocked the star, the telescope detected several brief dips in the star's brightness. The same pattern repeated when the star reappeared from behind the planet. These regular fluctuations lasted only seconds, yet forever altered our understanding of Uranus. The observation team was initially perplexed, as none of Uranus's known moons could account for these fleeting brightness changes. After careful analysis, scientists reached a bold conclusion. These brief dimming events were caused by a series of narrow ring systems orbiting Uranus. As these rings passed in front of the star, they acted like cosmic blinds, temporarily blocking portions of starlight. This serendipitous discovery revealed 9 distinct rings, later designated as the 6, 5, 4 alpha, beta, eta, gamma, delta, and epsilon rings. Each ring exhibited a perfectly circular orbit and remained parallel to the planet's equatorial plane. This discovery made Uranus the second solar system planet, after Saturn, to be confirmed as having a ring system. The precise timing data from this observation also enabled scientists to calculate the exact positions and widths of the rings. Most astonishingly, these rings are exceptionally narrow, some only a few kilometers wide, yet detectable from tens of thousands of kilometers away. This proves they possess well-defined boundary structures. The ingenuity of the occultation method lies in its ability to detect ring structures, even when the ring material is too sparse or dark to be directly imaged. Their blocking effect on starlight can still be precisely recorded. This method was later widely applied to study the ring structures of other planets. This unexpected discovery not only rewrote textbooks, but also opened a new field of research. It reveals that the universe is filled with unexpected structures. Even around celestial bodies we thought we knew quite well may conceal astonishing mysteries. 1986 flyby of Voyager 2 and subsequent observations by the Hubble Space Telescope increased the known number of Uranus's rings to 13. Together, these rings form a highly intricate system, yet stand in stark contrast to Saturn's bright, magnificent rings. The most striking feature of Uranus' ring system is its extremely low reflectivity. The geometric albedo of this ring material is a mere 0.03, darker than coal. This means they reflect almost no light, They can only be detected indirectly by the way they block background starlight, or directly through specialized image enhancement techniques. The composition of the rings has become a primary focus of scientific research. Spectral analysis indicates these rings likely consist of a mixture of water ice and dark organic matter. These organic compounds may include tholins, complex organic compounds commonly found on extraterrestrial bodies in the solar system. These substances, subjected to prolonged bombardment by cosmic rays and solar ultraviolet radiation, have developed this uniquely dark surface. The structure of the ring system is exceptionally complex. Some of the 13 rings exhibit perfect circularity, while others exhibit slight ellipticity. The widest epsilon ring varies between 20 and 100 kilometers in width, while the narrowest ring measures less than 1 kilometer. This extreme narrowness suggests the presence of undiscovered small satellites acting as shepherd moons. To maintain the ring boundaries, the particle size distribution of the rings is also distinctive. Unlike Saturn's rings, which are rich in fine particles, Uranus rings primarily consist of particles ranging from centimeters to meters in size, lacking micrometer-scale dust capable of effectively scattering light, which is one reason they appear so dark. Most strikingly, these rings exhibit mysterious periodic brightness variations, with certain segments noticeably denser than others, forming knot-like structures. These features may result from gravitational perturbations by undiscovered small satellites, or represent gravitational instabilities within the ring material itself. #######7.3 Comparison with Saturn's rings. Why Uranus appears like a cosmic shadow. Comparing Uranus rings to Saturn's helps us understand the diversity of planetary ring systems. Though both orbit ice giants, they exhibit strikingly different characteristics in nearly every aspect. Saturn's rings consist primarily of pristine water ice. Their remarkable reflectivity makes them easily observable even with small telescopes. In contrast, Uranus's rings resemble cosmic shadows, remaining elusive even to the most advanced telescopes. This disparity in reflectivity stems from differing constituent materials and reflects the fundamentally distinct formation and evolutionary histories of the two systems. In terms of structural scale, the Saturnian ring system extends over 280,000 kilometers, encompassing countless intricate features and gaps, while the Uranian ring system is relatively compact, with its outermost ring lying only about 50,000 kilometers from the planet's center. This compact structure may be related to Uranus's stronger gravitational field, or suggest the relatively young age of these rings. The rings' dynamical characteristics also differ markedly. Saturn's rings exhibit complex density waves and bending waves, indicating active dynamical processes, while Uranus rings appear relatively tranquil, with primary dynamics stemming from orbital resonances with its moons. This disparity likely originates from differing satellite distributions within the two systems. The most fundamental distinction may lie in the rings' origins. Saturn's rings likely formed from a shattered icy moon, while Uranus rings may have originated from collisions between moons, or the remnants of comets torn apart by tidal forces. These differing formation mechanisms have shaped the two systems' distinct material compositions and optical properties. The dark nature of Uranus's rings also provides a unique window for studying dark matter within the solar system. The organic matter within these rings may preserve crucial information about the early chemical evolution of the solar system, helping scientists understand the distribution of life precursors throughout the cosmos. When we gaze upon these two ring systems, we witness a perfect display of nature's diversity. One bright and dazzling like a diamond necklace, the other deep and mysterious like cosmic shadows. Yet both obey the same physical laws, quietly narrating the evolutionary story of planetary systems from their respective orbits. Uranus, perpetually tilted on its side, has forged a cosmic enigma rife with contradictions within our solar system. Beneath its serene, azure exterior surges a superstorm racing at 900 kilometers per hour. Its frigid, frozen world harbors paradoxes defying thermodynamic laws. Its seemingly languid rotational path actually bears the imprint of primordial violent collisions. These contradictory traits render this ice giant both unsettling and fatally alluring. Within planetary science's lineage, Uranus occupies an irreplaceable, unique position. It stands as our sole close-up sample for understanding the ice giant class. Its tilted magnetic field and frigid interior provide a critical testing ground for planetary formation theories. Each new study of Uranus expands the frontiers of human knowledge. Though decades have passed since Voyager 2's fleeting glimpse, a new era of exploration is dawning. NASA's proposed Uranus orbiter and lander mission is poised to launch toward this pale blue planet in the 2030s. It will probe the depths of its mysterious superocean, unravel the origins of its warped magnetic field, and perhaps finally unlock the energy secrets of its extreme storms. As we gaze upon this familiar starry sky, remember that pale blue speck tilting sideways. It is not only the most perplexing object in our solar system, but also a key to unlocking the mysteries of planetary system evolution. The universe is always more wondrous than we imagine, and Uranus stands as the ultimate testament to this wonder.